Hello, CS112. Today I'll be going over a quick solution to homework 6, which has to do with recursion. The rumors are true, by the way. I will be doing both of these tasks without using any helper functions or global variables or modifying the function signature, which I don't even think would have worked with a tester. But anyways, as you can see here, my solution for fill was 11 lines of code, and my solution for descendants was 7 lines of code. Keep in mind, this only involves the code and not the actual comments in there. So in this case, I would not count this comment as a line of code. And I will timestamp each of these videos in case you guys want to come back to them in your studies. So let's just dive right into it. I'm going to paraphrase fill for you. So fill, you'll be given a grid, which is a 2-dimensional list of integers. You're going to be given an old value, a new value, and a seed. This seed can act as your starting coordinates within your grid. What you want to do at your starting coordinates is check your current coordinates along with all the other neighbors for old values and change them to new values. So pretty much you're going to start here, you're going to plant your seed, you're going to check your neighbors for old values, plant your seed, check your neighbors for old values, plant your seed. Now what is a neighbor? This was addressed fairly early on in Piazza for those of you who started early, but let's imagine 5 is enclosed in the seed. 5 is our seed at coordinate 1, 1. All of these other numbers are going to be your neighbors, right? You have a neighbor up, left, down, and right, and diagonals as well. So that counts as 8 neighbors. Now, in order to access these neighbors, all you need to do is modify your current seed by 1. You're either going to plus 1 to the row or minus 1 to the row. Plus 1 to the column, minus 1 to the column. So let's look at an example. If I wanted to check directly to the right, all I need to do is return row and then column plus 1. Let's imagine I wrote row, column plus 1 right there. Row, column plus 1, because I'm staying in the same row. I'm staying in the same row 1, but my column has increased to 2. If I went down to the left, I would still be changing my column, but I would also be changing my row. So it looks like any of the diagonal movements, I'll be subtracting or adding 1 to both of my row and columns, but if it's more of a stagnant directly down, up, left, or right, I will be just adding or subtracting from 1. So while doing this my first time through, I did write down what each of them checked because you needed to check them in a specific order for this function to work. So as you probably have guessed by now, our recursive case is going to involve planting your seed and checking your neighbor, planting your seed and checking your neighbor. And since you have 8 neighbors, we're going to have 8 recursive cases. So typically when you do start out with a recursive problem like this, you want to think of base cases or and recursive cases. In this case, the base case is not really shouting out at us, so we're going to start with the recursive cases since we've already defined it. Over here, I have initialized 4 variables. This is just so it's more readable. So I went ahead and I indexed seed to grab the current row and column. As you can see, row is set to the first number and column is set to the second number. But I've also created a max row and a max column where I took the length of the grid minus 1 for max row and the length of a sublist row minus 1 to get the length, the max column length of the grid. Now, what does this do for me? Well, I need to check if I'm in bounds. Let's say I'm at this 2, the seed right here. I can't access these 3 neighbors. I'm missing 3 neighbors. So, well, that was a bad example, but I need to stay in check here. So let's say I'm at this 8 and I try checking these 3 neighbors. I can't because it exceeds my max row. My max row is going to be 2, if that makes sense. So I'm pretty much just keeping in bounds on this side and on this side. For these 2 sides, I may as well talk about it now, but if my row or column is less than 0, if it ever gets to a negative row and column, they don't exist, and that will protect me on these sides. And I'm not going to initialize a variable for 0. That makes no sense. But yes, I initialize these 4 variables to make my code more readable. So if I wanted to make my code ugly, I could technically have 10 lines of code here. But now let's talk about our recursive case. So our recursive cases obviously are going to involve planting our seed, checking your neighbor, planting your seed, checking your neighbor. Because in order to come up with our recursive cases, we needed to look at the problem as a whole. What are we trying to do? We are trying to fill up all the neighbors and neighbors of old values into new values. So breaking that problem into smaller problems, small equal problems, would simply be planting your seed, checking your neighbor, planting your seed, checking your neighbor. So, excuse me, I'm going to go ahead and mark that stuff down. So I'm going to say plant seed and check neighbor. That's probably how you spell it. I'm really bad at spelling, guys. But there was one thing that I brought up. I want to make sure I am in bounds. And also, if I check this 6, I don't care about it. It's not an old value. We're only hating on old values here. So we want to make sure that it is not only in bounds, but it is an old value. So we need to check if in bounds and if old value. So it is very important that we check if it is in bounds first. Now, why is this? If I try checking if it is an old value first, let's say I do the classic if, what is it, grid row call is equal to an old value, and then I start checking if it's in bounds, this could be out of bounds, right? I could be first checking if it's out of bounds, and it will throw an error. It will never even get to seeing if it is in bounds in the first place. So I'm just going to for now, just move this down here and check if it's in bounds. Now, I'm going to be using a method that I actually read about on my own when I was trying to come up with an easier way to stay in bounds when working with a multi-dimensional object, such as this list. And I forgot exactly what it's called, but it has to do with using an if-not statement. And for the very first step is you want to comprise a list of things that will cause you to go out of bounds. So what would cause me to go out of bounds? Let's think about the rows first. So if I have a row, and I'm going to pull this up again. If I'm at a row, I'm at row 0, for instance. If my row is less than 0, right up here, like I said before, that will cause an index out of bounds. So if row is less than 0, I'm going to add some spacing so it's readable. If row is less than 0, that will cause an error. If row is greater than my handy-dandy variable up here, max row, right? So if row is greater than max row, that doesn't make sense because that doesn't exist. That will also cause an out-of-bounds error. Now my column is very similar. In fact, it is the exact same thing, except working with columns rather than rows. Col can also not be greater than max col. Again, if column is less than 0, it will be over here, which doesn't exist. And if it's greater than our max col, it will be over here, which does not exist. So all I'm going to be doing, the structure of this if not statement will be if not, parentheses, and then I'm going to pretty much copy and paste each of these statements separated by an or statement. Okay. Row less than 0, or row is greater than max row, or col is less than 0. If I can type, that would be ideal. Or col is greater than max col. So that's beautifully going to check pretty elegantly if you're within bounds all the time in your recursive calls. And I'm not going to go too in depth of exactly what's happening here. It's pretty straightforward in my opinion, but if you want to pick it apart on a piece of paper or something, it will make more sense that way if this is not making sense to you. And keep in mind, I do have a second part to what this statement was saying. That is simply going to be this bad boy right here. I'm going to have an and statement because we need to check if it is, let me delete these guys real quick. We need to check if it's in bounds, which I've already done, and if it's an old value, and that's simply if the grid is the old value, because we don't care about other values. So again, very first thing we're going to do, now that we're pretending right now, the code will only get this far if we have both a valid coordinate and if it's an old value. So we want to make the in-place modification, which is required. So we're going to say grid at the current row and column that we are judging right now is going to equal the new value. That's all we need to do to plant our seed. And this is the incorrect equal sign. That will simply check if they're equivalent, but this will actually assign a value. Now we need to check our neighbors. Now, this is where all your recursive cases are going to be. So now let's think about a recursive case. So I'm just going to copy and paste our function signature for now, because this is what we're going to be calling within our function. That's what recursion is. But let's think about what's going on here. So I'm copy and pasting that. What are we changing here to make it recursion? Because we do have to change something or else we'll get infinite recursion. I have already modified the grid in place, so now the grid is different. Are we going to be changing the old value and the new value? No, right? Because we need to stay consistent and move through the list, checking for old values and replacing them with new values. But we do need to replace our seed. Now our seed is where we start at, and since our small steps are plant your seed, check neighbor, plant seed, check neighbor, we're going to need to move to that neighbor. So I'm going to make this a tuple, remove that word seed, and I'm actually going to modify it. So right now I'm going to check, I'm going to add some better spacing here, column +1. This is going to check directly to the right. I am now checking directly to the right to try filling that guy. Now I am going to, I am going to check all the more obvious directions, so up, down, left, right, before I get into the diagonals, and there is a reason for that, and I'm sure that you guys understand that. So the next one I will be checking is to the left, and I am just going to sort of try and power through this, not really explain too much as I'm going, because I mean, I'm literally just checking all 8 sides. 1, 2, 3, 4, 5, 6, 7. I'm literally just checking all sides, where the last 4 I'm checking for the diagonals. So that's exactly what I'm doing. Here I am now going to be checking the ups and the downs. So here I'm going to check down here. Oopsie daisy, I don't know what that is. And above I'm going to be checking, this is going to be down. And then this is up, because it works that way with rows and columns. And so for here, I'm going to have to modify the row and the column to check diagonals, right? I explained earlier in the diagram about that. So I'm going to say row +1, column -1. I'm going to say row +1, if I can type theoretically, and row and column +1. I gotta hit all the places. Now I need to check 2 minuses, column -1 and -1 and +1. Beautiful. So I know you're thinking to yourself, Ridge, this is already 11 lines of code. Well, let me tell you here. You guys don't even need a base case, all right? In this type of question, why is this here? What is this? Starts really bothering me. Why is there just a random bracket there? I'm going to delete it. I don't know if it'll break anything, but I'm going to delete it. Okay, so I know what you're thinking. Got 11 lines of code, but there's no base case yet. Well, that's because we don't need a base case. As you can see here, we're not even returning anything. So if we get to a coordinate that's not within bounds and all this jazz is, it's not even an old value, it'll simply stop. We're not returning anything. None of these will even get hit. Nothing will be changed, and our list will have been modified in place. So this is all we need. Let's go ahead and first I'm going to comment this out, or else you'll get an error, because it's just an empty definition. And I'm going to control S that. I'm going to run my terminal. I'm going to CD to my proper place. Go to Python. I'm going to go to the tester. Hopefully I have it here. Oh, I saw it. And I'm going to go to my homework6.py. And I'm going to type in fill. As you can see, beautiful, it works perfectly. Again, you guys, if this was not making much sense to you, I either suggest it's either probably this part right here or these guys. I think these guys are pretty straightforward, but still, if you go to Python Visualizer, you can literally follow the stack trace within the program. It will make it very clear to you. That's why I love Python Visualizer. So I'm just going to move right on to the next one, which is descendants. So this one, I'm not going to lie, I too had to read this a couple times because I was like, I was kind of half reading it. But pretty much, you're given a family tree, you're given a name. This name is a name of somebody, obviously, and you're given a distance. you want to compile a list of all the people who are the distance away from the name in the family tree. So let's just look at the very first example here. You're given the name Alex. You want to find all the people who are the length 2 away from Alex. So let's see here. You start at Alex. You have Bob, Chloe, and Dan. So obviously, these guys are 1 distance away from Alex. Now, we find each of their children. So this is Bob, we're still 1 distance away. This is 2, Ellen is 2 away. Philip, with an F, and Greg are 2 away. Hector, Iris, and Jason are all 2 away, because all these guys are 1 away, and their kids are going to be 2 away. That's why, the end list is compiled here. So now this, I'm not going to lie, once I actually understood what it was asking, this was pretty simple, in my opinion. Obviously, I've taken this course, so again, I typically do base cases first, but the recursive case just seems easier to me. What I would do is, obviously I noticed that we're returning a list of strings, so I would initialize an empty list of strings here called fam, because that's the fam we're trying to find. This is the I'm just going to comment this so we all know what it is. This is going to be the list of strings of family distance away. We know what that means. We know what that broken sentence means. And this is essentially going to be my return list. This is the list I'm returning at the end. So the first thing I want to check, obviously, is going to be to validate if the name is in family tree, because let's say we wanted to do, let's say Alex and then 4 or 5. Obviously, that wouldn't even make sense. We'd get to like Chloe, we'd get to, as you can see here, we'd get to Chloe, who is 1 away, we get to Philip, who's 2 away, then Philip stops. So there's not even, the name's not in list, so it should stop. We should not start adding it to our fam list. So I want to check first if the name is in the family tree. Now, I will explain what this means real quick, simply for those of you who aren't super familiar with dictionaries. I'm simply checking if this name, which is a string, is a key in the family tree. This will check all the keys. This will not check the values. There's a different way to check the values, which you guys should know. So now I'm going to create a for loop so I can iterate through the specific value pair. So in this case, I'm going to be first iterating through the Bob, Chloe, and Dan list. So for members, because these are members of the family in a family tree, and then name. This is how you iterate through the values, because the values happens to be an iterable object. Now this is where I get super fancy. Not really, but I'm going to be calling descendants recursively within my for loop. And how am I going to do that? An interesting property with lists, as you guys know, if you have a list, let's say bridge, and then you have plus, let's say, a random name like egg. If I say, if I try printing ridge plus egg, or I even say ridge plus equals egg, it will give me the value of sorry guys, brain dead, I'm studying for finals 2, and egg. That's what we'll return. So I'm compiling a list like this. I'm not even going to use append. I'm going to say fam plus equals, and then I'm going to call my function recursively. Descendants, oh thank God, I had to spell that for a second. Family tree, because my family tree will still remain the same. My members, I'm going to be calling it with the members now. So why am I calling it with the members? So my members is going to act as my name now. So I'm going to iterate it through every single one of the members. So a way to think about it is I'm going to iterate through this entire thing acting as if this was the original name I was passed. However, because I'm doing that, did I spell that? Members. Okay. Because I'm doing that, because I'm now pretending like I was past Alex in the first, or Bob in the first place rather than Alex, I'm going to do distance -1. And it will, because it's in a for loop, once it, if it actually finds a value where distance is equal to 0, it will concatenate to this. But if it doesn't reach, like if it says Alex 4 and we get to that Philip who doesn't have any kids, it won't add anything. Because, I mean, that's just how the recursion will work once I add my base case. Now, as I said before, my base case is when distance equals 0. So, let me... Oh my god, my back. Okay. Base case. So, as I explained before, if I ever get too far in the family list, or like, let's say my distance equals 0 and I still haven't found anything yet, I'm simply going to say distance equals 0. I'm going to return the name, except I need to put this into a list because that's what we're working with here. I'm going to listify name. So name is a string. This is simply going to become a list of strings. And obviously, I am returning something at the end. So in this indentation after my if and for loop, I'm going to return fam because that is what I'm working with here. Let's go ahead and Control S this bad boy, so that saves it. So I'm going to hit the up arrow key to get all my previous command line arguments in. I'm just going to delete it and run it. So I passed all the tests. Now I am going to go deeper into what just happened here because I feel like this specifically might confuse some of you guys. So I'm just going to go to Python Visualizer and I'm going to paste this code here. So what will be the easiest way to do this? I'm going to copy and paste this right here, and we can follow the stack trace together. Oh no! Let's see if we can find it. Ew, there's not a comma there. Disgusting. Okay, beautiful. I should have printed it, so I'm just going to say x equals that, and then I'm going to print x. So now it's going to print out the correct answer, obviously, and as you can see here, if I can get all of it, there we go, it prints out the correct list. So let's follow this stack trace. This is what I'm talking about. So I'm going to go to my first thing. I'm actually going to click through a lot. So what it's doing, once it gets in this first loop, first of all, it recognizes that name, which is currently Alex. Make it full screen. Name, which is currently Alex, is in family tree, which is my dictionary of stuff right here. And it's going to say for members in family tree name. So now it's iterating through family tree name, which is Alex, which is name. And now that we're in family tree name, we're iterating through this. And as you can see here, when I recalled the function, my recursive call right here, I made members, which is my current member, the new sort of head of the family, the new name here with a distance -1. So let's continue going here. As you can see here, we start with Alex. We're looking at a distance of 2, but we found Bob. Bob now had a distance of 1. So once we get to that distance of 0, so we find Ellen. Ellen has a distance of 0 because, as you can see, we get to Bob, who has 1 kid. As we transfer to this kid, we do distance -1, and we've gotten 0. And once we get, I'm just going to move further down the line. Okay, we're at Hector now, which is, let's get to Jason. Okay, we're at Jason now. So I've skipped through us getting to Chloe, which is the second iteration of this for loop, and checking all of Chloe's kids. And then I've gotten to Dan, checks all of Dan's kids. So now we're at Jason, who has a distance of 0. It should be, yep, Jason has a distance of 0. And because he has a distance of 0, we're returning name. So each of these return names, every single time we get to a kid that has a 0, the distance of 0, we're returning it as a list. Whoopsies. And I'm plus equaling it here. I'm doing that thing I described with Ridge, and I don't even remember what word I picked. But if you do a list plus a list, and the 2 elements are strings, you will have a list plus a list. I don't know how to better explain that, but you guys saw it a couple minutes ago. So I'm plussing it with whatever list I got here. So I'm just going to keep adding it to name after name after name. And so on and so forth. And we return fam at the ends and print it, obviously. And we get what we want. Did I? Yeah, I think it was only 2 functions. Yeah, okay. So that concludes the video. I hope that this was helpful for you guys. I'm unsure of whether there will be a video made of classes in object-oriented programming because of some students have doctor's notes and other maybe some disabilities that allow them to have longer run assignments, and I cannot post a video solution while they still have time to turn it in, or else they can just copy my code. And I also don't think it would be fair for me to post one on Wednesday when half of you guys have already taken the final exam. Good luck on your exam, guys, and have a great summer.